Module 4, Lecture B, Transforms and Augment. By the end of this lecture, you will be able to apply common preprocessing transforms such as normalization, resizing, and tensor conversion to raw data. Design and configure data augmentation pipelines that improve model robustness without corrupting labels. And integrate transforms into dataset and data loader workflows while monitoring their impact on training. Core preprocessing transforms, tensor conversion and normalization. In deep learning, the first step is to convert raw data into tensors, which are the basic data structures that models use. Original data such as images, audio, text, or tables in formats like CSV or JSON are good for storage, but not efficient for GPU computation. Turning them into tensors creates structured arrays with consistent shapes and data types, which makes batching and moving data between devices efficient. This conversion is essential for smooth neural network training, improving both performance and reproducibility. After converting your data into tensors, an essential next step is normalization, which greatly affects how efficiently a model learns. Normalization adjusts raw values to a controlled range, often centering them around 0 with a consistent spread. For instance, image pixel values that originally range from 0 to 255 are rescaled so that each channel has a stable mean and variance. In tasks like satellite image classification, this prevents features with large raw values from dominating the gradients and helps the model focus on meaningful patterns such as edges and textures. Treat tensor conversion and normalization as one integrated step in your preprocessing pipeline. First, convert all data samples, such as images or audio, into tensors with a consistent format. Then, normalize them using the same mean and standard deviation computed from the training data. Applying this uniform normalization across both training and validation sets helps prevent distribution shifts that can hurt model performance. This combined approach creates a stable foundation for further preprocessing and leads to models that train efficiently and generalize well. Python code, tensor conversion, and normalization. This material introduces the basics of converting data into tensors using TensorFlow, with a simple focus on image tensors. It explains how raw image data is turned into tensor form so it can be processed by TensorFlow. The main emphasis is on the steps for converting the data and then normalizing it so the values are in a suitable range for further computation. Overall, it provides a brief foundation for working with image tensors in TensorFlow. The comment about installing TensorFlow is a reminder to make sure this library is available in your programming environment before running the script. You typically install it with a package manager, such as pip. This setup step is necessary because the rest of the code depends on TensorFlow to create and manage tensors. It also uses TensorFlow to perform key operations like converting data and normalizing values. We begin by importing 3 common libraries, one for working with the operating system, one for generating random numbers, and one for mathematical tools. The operating system library lets the program handle files, folders, and other system-level tasks. The random library is used to create random values, which are helpful for generating data or running tests. The math library provides mathematical functions and constants needed for more complex calculations in the code. We begin by importing TensorFlow and NumPy, 2 key libraries for numerical computing and working with tensors. TensorFlow is used to build and train machine learning models and to create and manipulate image tensors. NumPy supports large, multidimensional arrays and matrices and provides many mathematical functions to operate on them. In this script, TensorFlow handles the image tensor operations, while NumPy is used for numerical tasks such as setting random seeds, to ensure reproducible results. We begin by setting a fixed random seed with the value 42, so that any random operations give the same results every time we run the code. We apply this seed to the standard random module, so its generated numbers are consistent. We also set the seed for the NumPy random number generator, which controls randomness in NumPy operations. Using the same seed across these libraries ensures reproducible and uniform results. We set the random seed in TensorFlow using a stored value so that any random operations behave the same way every time the code runs. This makes the results consistent across runs. Such reproducibility is important for running experiments, comparing models, and debugging issues reliably. This line checks and announces which version of TensorFlow is currently in use. It provides a quick way to confirm the installed version of the library. Knowing the exact version is important because different versions may behave differently. This helps with both compatibility and debugging when working with TensorFlow. We create a small fake RGB image by setting its height and width to 4 pixels and using 3 channels for red, green, and blue. Then we use TensorFlow's random uniform function to generate a tensor with this shape, filled with random integer values between 0 and 256 to represent pixel intensities. The tensor is stored with a 32-bit integer data type, which is appropriate for holding these raw pixel values before any further processing. We take a tensor of random integers and convert it to an unsigned 8-bit integer type, so it matches standard image data. This type is commonly used to store pixel values from 0 to 255. Making this conversion ensures the data is interpreted correctly as image pixels. It is an important step before performing further image processing tasks, because it aligns the tensor with common image formats. The code prints the shape and data type of the fake image tensor to confirm that the image is set up correctly before any transformations. The shape tells you the image height, width, and number of color channels. The data type shows that the image is stored as unsigned 8-bit integers, which is the standard format for raw image data. This step converts the fake image data from unsigned 8-bit integers to 32-bit floating point numbers using a TensorFlow image conversion function. During this conversion, pixel values are rescaled from the original range of 0 to 255 down to a range between 0 and 1. Doing this prepares the image for later processing, such as normalization. It ensures the data type and value range are consistent, which is important for accurate computations in image analysis tasks. We first confirm that the converted image tensor now uses the float32 data type, showing it has been successfully changed from its original unsigned integer format. Then, we check the minimum and maximum values of the tensor after scaling, using TensorFlow functions that compute the overall lowest and highest pixel values. This lets us verify that the pixels now fall within the expected float32 range, typically between 0 and 1. Together, these checks ensure that the image data has been correctly converted and normalized for further processing. We set the mean for each color channel as a TensorFlow constant with a value of 0.5 for red, green, and blue to establish a baseline for normalization. We also define the standard deviation for each channel as a constant with a value of 0.2. Together, these values describe how the pixel intensities are centered and spread out. Using them, we can normalize the image data by centering it around the mean and scaling it according to the standard deviation. Before normalizing an image tensor, We reshape the mean and standard deviation tensors so they match the image's dimensions, with 1 by 1 by 3 values for the 3 color channels. This matching shape allows them to be broadcast correctly across the image data. As a result, the mean and standard deviation are applied smoothly to each color channel during normalization. We normalize the image by subtracting the mean from each pixel value and then dividing by the standard deviation. This transforms the pixel values so they have a mean of 0 and a standard deviation of 1. Doing this is a common preprocessing step in machine learning. It helps ensure the data is centered and consistently scaled, which makes model training more stable and effective. To check the statistics of a normalized image, we first use TensorFlow to compute the mean value across all pixels, which tells us the average intensity and gives a sense of the image's central tendency. We then use TensorFlow's standard deviation function to measure how much the pixel values vary around that mean. Together, these two statistics help confirm that the normalization process was applied correctly and that the pixel values have the expected distribution. We print the approximate mean of the normalized image tensor to check its central tendency after normalization, and we print the approximate standard deviation to see how spread out the values are. Together, these statistics confirm whether the normalization worked as intended. In most cases, we expect the normalized data to be centered around 0, with a standard deviation close to 1. The code prints the shape of the normalized image tensor to confirm that normalization has not changed the image's original dimensions. This check ensures that operations like scaling and normalization preserve the spatial structure of the data. Verifying the shape in this way is important so the image remains valid for later processing or analysis. This script shows how to convert and normalize image data using TensorFlow. It first sets a fixed random seed so the results are reproducible, then creates a small fake RGB image with random pixel values stored as unsigned 8-bit integers. The image is converted to a float tensor, and the pixel values are scaled to lie between 0 and 1. Next, the script normalizes the image by subtracting a mean of 0.5 and dividing by a standard deviation of 0.2 for each color channel, producing data with an approximate mean of 0 and standard deviation of 1. It also prints the TensorFlow version, data types, and tensor shapes to confirm that the normalization keeps the original image dimensions unchanged. Spatial resizing basics. Spatial resizing is an important preprocessing step in computer vision because images from different sources often have different sizes, but neural networks require inputs with the same dimensions. By resizing each image to a standard resolution, such as 224 by 224 pixels, we can convert them into uniform tensors that the model can process efficiently. This involves stretching or shrinking the pixel grid to match a fixed template while trying to preserve as much detail as possible. Consistent resizing prepares images for later transformations and model operations. When resizing images, your choices directly affect how much detail is kept or lost. Shrinking a high-resolution image can remove small features, which might be acceptable for broad tasks like land classification, but not for detecting tiny objects. Enlarging a small image does not create new detail. It relies on interpolation, which can smooth edges or introduce artifacts. Therefore, select the target image size based on your model's requirements and the smallest features that matter, such as using lower resolution for simple digit recognition and higher resolution when subtle textures like those in plant disease detection are important. When resizing images, it is important to keep the aspect ratio and composition so shapes are not distorted and visual cues are not altered. Simply stretching a rectangular image into a square can create unnatural results and cause models to learn incorrect patterns. To avoid this, preprocessing usually resizes images proportionally and then uses cropping, padding, or center cropping. This keeps images from different sources realistic and consistently scaled, preserves spatial integrity, and allows later transformations to work properly. Python code, spatial resizing basics. This script introduces the basic idea of spatial resizing for images. It uses TensorFlow to safely change the size of simple example images. The main goal is to observe how resizing affects image shapes, aspect ratios, and overall visual appearance. By focusing on these changes, you can better understand the impact of different resizing choices. The line that begins with a hash and an exclamation mark is a pip command to install TensorFlow, a Python library needed for the image processing tasks in the script. Pip is a tool that lets you add libraries that are not included in standard Python. Because this line is commented out, it will not run unless you remove the comment symbol. It is included mainly as a reminder for users to install TensorFlow if it is not already on their system. We begin the script by importing a few standard libraries that we will rely on throughout. The operating system library lets us interact with the system, for example, to work with files or environment variables. The random library provides tools for generating random numbers and controlling randomness, which is important for setting seeds and making results reproducible. Finally, we import a numerical computing library that efficiently handles arrays and mathematical operations, forming the core of our data processing in this script. We begin by importing TensorFlow, a library that provides powerful tools for machine learning and deep learning, especially for working with images. We also import the datasets component from the keras part of TensorFlow, which gives us easy access to common datasets such as MNIST. Using these imports, we can load, resize, and process image data efficiently. This setup prepares us to demonstrate image resizing techniques on the MNIST dataset. We start by setting a fixed seed value for the random number generator so that our results are reproducible. This ensures that every time we run the script, the same sequence of random values is produced. Having consistent random output is important for debugging and testing because it lets us reliably compare runs. We use the random library to set this seed, so all random numbers from that library follow the same predictable order each time the code is executed. To get consistent results every time you run your code, you should set the random seed for both NumPy and TensorFlow. Setting the seed in NumPy makes its random number generation deterministic, so it produces the same values on each run. Using the same seed value in TensorFlow's random settings does the same for TensorFlow operations that involve randomness. This practice is essential for reproducibility, especially when training models or running experiments that rely on random processes. We begin by printing the TensorFlow version in use to verify the environment is set up correctly. This helps confirm that the installed version matches what we expect. It is important because different TensorFlow versions can have different features or behaviors. Knowing the exact version also makes it easier to debug issues and ensure compatibility with the rest of the code. We begin by loading the MNIST dataset, which consists of small grayscale images of handwritten digits, commonly used to train image processing models. The loading function returns two sets of data, one for training and one for testing. We keep only the training images and their labels, assigning them to our training variables, and ignore the test set for now. This lets us focus on a subset of the data for demonstration purposes. To explore image resizing techniques, we first select a small subset of images from the training data. In this example, we choose 4 samples and take the first 4 images from the training set. We store these images separately so we can experiment with them more easily. Working with this small, manageable group helps us focus on understanding and demonstrating the resizing process. We first convert the selected NumPy images into TensorFlow tensors with a float32 data type, so they work correctly with later TensorFlow operations. Then we add a channel dimension to these tensors. This extra dimension is needed because even though the images are grayscale, many image processing functions expect inputs to include a channel dimension, whether there is one channel or several. We first print the shape of the original batch of images to confirm it matches what we expect. This check verifies that the images were loaded correctly and have the right format. By doing this, we make sure that any resizing or later processing steps are applied to the correct data structure. It is a simple but important step to prevent errors in the workflow. We set a target spatial size for our images by choosing a height and width of 56 pixels. This means every image will be resized to 56 by 56 pixels. Doing this ensures that all images have a consistent size, which is important for any later processing or analysis steps. We use TensorFlow's image resize function to scale images to a height and width of 56 by 56 pixels. The resizing method is bilinear interpolation, which estimates each new pixel value from a weighted average of the 4 nearest pixels in the original image. This approach helps keep transitions smooth and reduces visual artifacts in the resized images. We now resize the images using the nearest neighbor interpolation method. This technique assigns each new pixel the value of the closest original pixel, without averaging nearby values. It is very fast, but can make the resized image look blocky. To do this in TensorFlow, we call the image resize function on the image tensor, provide the desired height and width, and set the interpolation method to nearest. We verify that the resized images have the correct dimensions by printing their shapes. First, we check the images resized with bilinear interpolation to confirm they match the target size. Then we repeat this check for the images resized with nearest neighbor interpolation. This confirms that both resizing methods worked correctly and that the images are now ready for further processing or analysis. We begin by computing the average pixel value of the original images using a TensorFlow function that takes the mean across all pixels in the image tensor. This result is then converted to a NumPy array, so it is easier to use in later numerical analysis. Establishing this average pixel intensity gives us a baseline for the original images. We can then compare this baseline to the averages from resized images to see how different interpolation methods affect the image data. We first compute the average pixel value across all images that were resized using bilinear interpolation, then convert this average to a standard Python number. We repeat the same process for the images resized with nearest neighbor interpolation. Comparing these two mean pixel values allows us to see how the different resizing methods affect the overall image data. We begin by computing the mean pixel value of the original images to establish a baseline. Then we calculate the mean pixel value after resizing the images with bilinear interpolation to see how this method changes overall brightness or darkness. We repeat this for images resized with nearest neighbor interpolation. Comparing these mean values shows how each resizing technique alters the image data. We begin by selecting the first image in the dataset and retrieving its label, converting that label to an integer so it is easy to read. We then examine the original image by printing its shape to understand its dimensions. After that, we resize the image using bilinear interpolation and print the new shape to see how the dimensions change. Finally, we resize the same image using nearest neighbor interpolation and print that shape as well, allowing us to compare how the two resizing methods affect the image dimensions. This script shows how to resize images from the MNIST digit dataset using TensorFlow. It first sets a fixed random seed. then loads a small batch of grayscale images and converts them to float tensors with a channel dimension. The images are resized to 56 by 56 pixels using both bilinear and nearest neighbor interpolation, and the script prints the original and new shapes to verify the change. It also compares the mean pixel values before and after resizing to illustrate how the two interpolation methods affect the data. Finally, it displays an example label and the shapes of one original and one resized image to make the impact of resizing more concrete. Channel and dtype basics. In deep learning, it is important to manage how channels are arranged and what data type they use when working with images or signals. Channels represent components like the red, green, and blue values in images, or different streams in time series data, and different tools expect these channels in different positions. Some tools place channels last, while many neural networks expect them right after the batch dimension. If this layout is wrong, the model can misinterpret the data and scramble colors or features. Making sure the channel order and dtype are correct is essential for accurate processing of medical scans, photos, and sensor recordings. Data types control how values are stored, their precision, and how fast computations run. Raw images often use 8-bit integers, but neural networks work better with floating point numbers because they can represent fractions and support optimization. During preprocessing, it is important to convert integer data to floating point tensors and scale values consistently, usually between 0 and 1, to avoid issues like integer division errors or incompatible operations. In applications such as satellite imagery or speech recognition, carefully choosing and managing data types helps balance precision, memory use, and speed, and ensures models behave correctly across different datasets and environments. When integrating data from different sources or preparing inputs for specialized models, it is important to choose consistent channel configurations and data types. Models that use both RGB images and depth data need a defined channel order and compatible types, so operations like convolution behave correctly. For grayscale images, you must decide whether to keep a single channel based on what the model expects. In medical imaging, high bit depth scans should be converted to standard floating point tensors while preserving intensity values. Overall, standardizing channel order and data types during preprocessing improves consistency and reduces errors across datasets and environments. Python code, channel, and dtype basics. This script introduces the basics of channels and data types in image tensors. It uses TensorFlow to examine simple image tensors, so you can see how their shapes are defined and how channel order is represented. It also demonstrates how to convert between different data types, helping you understand how these choices affect image data in practice. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the expected features and behavior of that release. This helps avoid problems that can occur if the library is automatically updated to a newer, potentially incompatible version. We begin the script by importing a few standard Python libraries. The operating system library is included for potential interaction with the system environment, even though it is not directly used in the visible code. We also import the random library, so we can generate random numbers and control them by setting a seed for reproducible results. Finally, we bring in NumPy, a numerical computing library that will be heavily used to create and manipulate arrays, especially for generating and working with image data in this script. We start by importing TensorFlow, which is the main library we use to build and train machine learning models. After importing it, we check and print the TensorFlow version that is currently installed. Confirming the version helps us ensure compatibility and verify that we are working with the expected setup for our code and experiments. We begin by setting a fixed seed value, such as 42, so that any random operations produce the same results every time the code runs. We apply this seed both to the standard random library and to the NumPy random number generator. Using the same seed for both ensures that all random numbers they generate are predictable and repeatable. This reproducibility is especially important for tasks like testing and debugging, where consistent behavior is required. We create a small fake color image using a numerical library by generating a 4x5 grid of pixels, each with 3 channels for red, green, and blue. Each pixel value is a random integer between 0 and 255, which matches the usual range for 8-bit images. The data is stored as unsigned 8-bit integers, so every color value fits within this standard image format. We begin by checking the shape of the NumPy image array, which tells us its height, width, and how many color channels it has. This helps us understand the structure of the image data we are working with. We also print the data type of the array, which here is unsigned 8-bit integers, a standard format for image pixels. Knowing both the shape and data type is important for any later image processing or conversion steps. We begin by converting the image from a NumPy array into a TensorFlow tensor, so we can use TensorFlow for further processing. After this conversion, we check and print the tensor's shape, which is organized as height, width, and number of channels. Confirming this shape ensures that TensorFlow is interpreting the image dimensions correctly before we continue with any additional operations. This code checks the size of the last dimension of a TensorFlow image tensor to find the number of channels. By doing this, it confirms that the image data is stored in height, width, and then channels order. Knowing that the channels are in the last dimension is important because many image processing operations expect this specific layout to work correctly. We first convert the TensorFlow image data type from an unsigned 8-bit integer to a 32-bit floating point format. This change allows more precise mathematical operations because it supports a wider range of values and decimal precision than the original type. After converting, we check and print the new data type to confirm the update. This step is important to ensure accurate results in later operations, such as scaling. The code normalizes the image tensor by dividing its float pixel values by 255, so they fall between 0 and 1. This scaling makes the data suitable for machine learning models that expect inputs in this range. After the transformation, it uses TensorFlow functions to compute and print the minimum and maximum values of the scaled tensor. This confirms that the pixel values are now within the expected normalized range. We are changing the order of the channels in an image tensor, from height, width, and channels to channels, height, and width. Using TensorFlow's transpose operation, we specify a permutation that rearranges the dimensions into this new order. After the transformation, we check the new tensor shape to confirm that the layout is now channels first. This step is important because some machine learning models require their input data in this channels, height, and width format. We verify that the number of channels in the image tensor stays the same after reordering its dimensions. After the transpose operation, the channels move to the first dimension, so we use an assertion to check that this new first dimension still matches the original channel count. This confirmation step is important because it ensures that the reordering process has not accidentally changed how many channels the data has. By doing this, we help maintain the integrity and reliability of the image data. We create a simple example of a grayscale image by defining a 4x4 grid, which sets both the height and width to 4 pixels. Using a random integer generator from a numerical library, we fill this grid with pixel values between 0 and 255, the typical range for image data. The result is a 2-dimensional array where each entry is an unsigned 8-bit integer, representing the intensity of a pixel in the grayscale image and making it suitable for basic image processing tasks. The code first converts a grayscale image stored as a NumPy array into a TensorFlow tensor so it can be used in TensorFlow operations. It then adds an extra dimension to represent the image channel, even though there is only one channel for grayscale. This added channel dimension makes the image match the standard format expected by many machine learning models. As a result, the image can be processed consistently alongside images that have multiple channels. We first print the shape of the grayscale tensor to see its original dimensions and understand how the image data is structured. Then we print its shape again after adding a channel dimension. This added channel makes the grayscale data consistent with typical image formats, which always include a channel dimension. By comparing the two shapes, we verify that the channel was successfully added and that the tensor is now compatible with operations that expect image data with channels. The script ends with a simple print message that confirms the demonstration is complete. This final message tells the user that the code has finished running and that the example of handling channels and data types in image processing has been successfully carried out. It serves as a clear wrap-up so the user knows all intended operations on the image data have been performed. This script shows basic image tensor operations in TensorFlow. It begins by creating a small random color image with NumPy, converting it to a TensorFlow tensor, and confirming its shape and data type in height by width by channels format. The tensor is then cast to floating point, and its pixel values are scaled to range between 0 and 1, with the new minimum and maximum values displayed. Next, the script rearranges the tensor so that the channel dimension comes first, while keeping the number of channels the same. It also demonstrates creating a grayscale image, adding a channel dimension to it, and printing the shapes before and after this change. The script ends by confirming that channel layouts and data types have been handled correctly. Designing safe augmentations. Safe spatial augmentations. Safe spatial augmentations are geometric changes to input data that keep the original label correct while adding useful variation. Examples include horizontal flips, small random crops, slight rotations, and modest scaling, which work well for natural image classification. These transformations teach models that position and orientation are not essential to the class, such as recognizing a cat no matter where it appears in the frame. By using such safe spatial transforms, models learn robust, high-level features instead of relying on fragile pixel-level patterns. When designing data augmentations, match your spatial transforms to the geometry of your data and the realistic variations in your task. In many vision problems, small shifts, modest crops that keep the main subject, and limited rotations are reasonable because they reflect how people normally see objects. For example, in traffic sign recognition or medical imaging, slight translations, scaling, or mild tilts can help models handle natural changes in camera angle or distance. However, extreme rotations or distortions that would not occur in practice can change the meaning of the image and break the label. Always choose augmentations that expand your training data while preserving label accuracy. When using spatial data augmentations, you must respect how each task defines label preservation. In image classification, a horizontal flip is usually safe, but in handwritten digit recognition, it can turn a 6 into a 9 and change the label. For object detection, any transformation must be applied consistently to both images and their annotations so objects stay aligned. In domains like satellite imagery or medical scans, even small geometric changes can distort important orientation cues. So only gentle transformations should be used. By understanding these differences, you can choose a safe set of operations that preserves labels while still increasing training diversity. Python code, safe spatial augmentations. Let's break it down. We have a Python code base. We're focusing on safe spatial augmentations. Safe means no unexpected changes or errors. Spatial means involving space or positioning. Augmentations means transformations or modifications to data. Now let's look at an example. We define a function. Inside that function, we apply a spatial augmentation, like a rotation or a shift. We make sure it's safe. We handle errors gracefully. We validate inputs before processing. This is the idea behind safe spatial augmentations. This script demonstrates how to apply safe spatial data augmentations using TensorFlow image tools. It focuses on simple and reliable transformations, such as flipping, cropping, and small rotations. These operations help modify images in controlled ways while preserving their essential content. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this specific version makes sure the code runs with the intended library. It helps prevent compatibility problems that could occur if a different TensorFlow version were used. We begin by importing 3 key libraries that prepare our script for data work. The operating system library lets us interact with files and environment settings. The random library allows us to generate random numbers to introduce variability into our data processing. Finally, the numerical computing library NumPy provides efficient arrays and many mathematical functions. Together, these imports supply the basic tools needed for data manipulation and augmentation in the script. We begin by importing TensorFlow, a powerful library used for machine learning and deep learning, so we can work effectively with images. We also import the datasets component from the Keras part of TensorFlow, which gives us easy access to common datasets for training and testing models. In this script, we use it to load the Cypher10 dataset, a standard collection of small images often used to train image classification models. We set a fixed seed value so that any random operations in our code always produce the same results, which is essential for reproducible experiments. To do this, we give the same seed to the standard random library, to the random number generator in NumPy, and to TensorFlow's random operations. Using a consistent seed across these libraries keeps all random processes aligned and creates a stable environment for testing and debugging. We quickly display the TensorFlow version in use to confirm which release of the library is running in the current environment. This simple check helps verify compatibility with our code and dependencies. It also supports debugging by making it clear exactly which TensorFlow version produced the results we see. We begin by loading a small subset of the Cypher10 image dataset using TensorFlow's dataset tools. Cypher10 is a standard dataset of small images grouped into 10 classes and is often used to train machine learning models. For a lightweight demonstration, we select only 8 samples from the training data. We slice both the images and their labels to include just these 8 examples, giving us a small, focused dataset to work with. The code prints the shapes of the training images and labels to confirm that the data has been loaded correctly. By checking these shapes, we can see whether the subset has the expected number of samples. This also helps verify that each image is properly matched with its corresponding label. In short, displaying the shapes is a quick way to validate the structure and alignment of the training data. The code converts the training images to floating point numbers and scales their pixel values so they fall between 0 and 1. This process, called normalization, prepares the data for use in machine learning models. By putting all pixel values on a consistent scale, it helps improve the model's performance and makes training more stable. This function safely performs a horizontal flip on an image by using TensorFlow's image utilities to randomly flip it from left to right. The randomness introduces variation into the images, which serves as data augmentation. This augmented data can help improve the robustness and performance of machine learning models. After the flip is applied, the function returns the modified image. This function performs a safe random crop on an image while preserving its final size. It first reads the image height and width, then computes a crop that is about 90% of each dimension, so the cropped area is slightly smaller than the original. Using TensorFlow's random crop operation, it extracts this smaller region while keeping 3 color channels. The cropped image is then resized back to the original height and width, and this resized image is returned as the output. This function applies a small random rotation to an image. It first uses TensorFlow to generate a random angle between -0.2 and +0.2, ensuring only a subtle change. It then calls a TensorFlow add-on's image rotation function with the image and this angle to perform the actual rotation. Finally, it returns the rotated image as the transformed output. To rotate an image using dense sampling, we first temporarily add an extra dimension so the image is treated as a batch of 1. We then call a rotation function on this batch, providing the image and the desired rotation angle. After the rotation is applied, we remove the extra dimension to restore the original image shape. The result is the rotated image, returned in the same format as the input. This function rotates a batch of images using an affine transformation based on a given angle. It computes the cosine and sine of the angle to build a flattened rotation matrix, converts it to a TensorFlow tensor, and reshapes it into the format required for affine transforms. This transformation is then duplicated so the same rotation is applied to every image in the batch. The function calls TensorFlow's projective transformation operation with bilinear interpolation for smooth results, and a reflect mode to handle image borders, and finally returns the rotated images with the same dimensions as the inputs. This function performs a sequence of safe spatial augmentations on an image to improve model robustness. It may randomly flip the image horizontally to teach invariance to left-right orientation. It then applies a small random crop and resizes the result back to the original size so the model learns to focus on different regions. Finally, it rotates the image by a small random angle within a set range to handle slight rotations. After these transformations, the function returns the augmented image. We begin by choosing the first image from the training dataset as our example for data augmentation. We then retrieve its label and convert that label into an integer so it is easier to work with. Finally, we print this original label to verify which category the image belongs to before applying any transformations. We create an empty list to hold augmented images, then run a loop 3 times to generate variations of the same example image. In each iteration, we adjust the random seed by combining the original seed with the loop index so the results are different but still reproducible. We then apply safe spatial augmentations such as flipping, cropping, and rotating to the image. Each augmented version is added to the list, giving us several slightly different images derived from the original. We first stack all the augmented images along a new axis to form a single tensor, which combines them into one batch that is easier to process as a group. After creating this batch, we check its shape to verify the expected dimensions. This confirmation helps ensure that the augmentation was applied correctly and that the images are properly prepared for the next steps, such as further processing or visualization. To display the original and augmented images together, we use the plotting library called matplotlib/pyplot. This tool lets us create visualizations so we can see both versions of the images at the same time. By plotting them side by side, we can easily compare how the augmentation has changed the original images. We create a figure in matplotlib with 4 subplots arranged in a single row, and set the overall figure size to 8 by 3 inches. In the first subplot, we display the original image and give this subplot the title Original, so it is clearly labeled. To keep the viewer's attention on the image itself, we remove the axis lines and labels from this subplot. We loop over 3 positions, one for each augmented image, and use the plotting axes to display the image at the current index. For each subplot, we set a title that says aug, followed by the index +1 to show its place in the augmentation sequence. We then turn off the axis lines and labels, so the viewer's attention stays on the images themselves. The code uses a layout adjustment feature from Matplotlib to make sure all parts of the plot fit clearly without overlapping. This automatic layout step cleans up the appearance of the figure. After that, the display function is called to show the plot, presenting the original and augmented images side by side so they can be visually compared. This script shows how to apply safe spatial data augmentations to a small subset of the CIFAR10 image dataset using TensorFlow. It first fixes the random seed so results are reproducible, then loads and normalizes 8 images. The script applies horizontal flips, small random crops, and slight rotations that change the images while preserving their essential features. By repeatedly augmenting one example image and visualizing it alongside the original, it demonstrates how these controlled transformations increase data variability in a way that supports training more robust machine learning models. Color jitter and noise. Color-based augmentations help models cope with different lighting and sensor conditions without changing what is in the image. By adjusting brightness, contrast, saturation, or hue, you can simulate environments like sunny or cloudy weather while keeping objects recognizable. However, these changes must stay within realistic limits so the images do not look unnatural. If the colors are pushed too far, important details can be lost, such as a tomato no longer looking like a tomato, or a medical image losing its diagnostic clarity. When setting up color jitter, match the strength of the changes to the typical conditions in your domain. For applications like autonomous driving, moderate adjustments to brightness and contrast can simulate different lighting, and small changes to saturation and hue can mimic camera variations. In more sensitive domains such as pathology or satellite imagery, keep all these adjustments very small to avoid losing important details. As a practical check, make sure a domain expert could still confidently label the augmented images. If not, the color jitter settings are likely too strong. Noise-based data augmentation adds small amounts of random noise, such as Gaussian noise, so models learn to rely on stable, generalizable features rather than fragile pixel-level details. This helps them perform better on imperfect inputs like grainy or compressed images. However, the noise level must be chosen carefully, because too much noise can hide important information, such as lesions in medical images. A practical approach is to start with low noise, compare performance with clean images, and increase the noise only while the content remains clearly visible and labels can still be assigned with confidence. Python code, color jitter and noise. This script demonstrates how to apply color jitter and noise as image augmentations using TensorFlow's image preprocessing tools. These operations slightly alter the appearance of images while preserving their original labels. The focus is on safe transformations that do not change the underlying class of the image, making them suitable for training robust machine learning models. The comment about installing TensorFlow is a reminder that you must have TensorFlow installed in your environment using the Python package manager. This is essential because the script depends on TensorFlow for image preprocessing tasks. In particular, it uses TensorFlow to apply effects like color jitter and noise to images. Installing TensorFlow ensures all required functions and classes are available, so the script can run correctly. We start by importing 3 key libraries for our script. The operating system library lets us work with files and environment settings. The random library allows us to generate random numbers, which is useful for setting seeds and adding randomness to data processing. Finally, we import NumPy, a numerical computing library that helps us efficiently handle arrays and perform mathematical operations throughout the code. We start by importing TensorFlow, a widely used library for machine learning and deep learning. Next, we import the Layers module from the Keras part of TensorFlow. This module provides the main building blocks for creating neural networks. It also includes image preprocessing layers, which we will use to apply transformations such as color jitter to our input images. We begin by choosing a fixed seed value, such as 42, to make our results reproducible. This seed is used to initialize the random number generator from the standard random library, so that any random operations give the same output each time the program runs. We also set the seed for the NumPy random number generator, which controls randomness and NumPy functions. Using the same seed for both ensures that all random behavior in our code is consistent across different runs. We set the random seed in TensorFlow so that any random operations it performs give the same results every time we run the script. This makes the behavior of random elements consistent across runs. Such reproducibility is important for debugging because it lets us reliably track down issues. It also ensures consistency in experiments, so results can be compared and trusted. This line displays the version of TensorFlow currently in use. Checking the library version is important because features and behavior can change between versions. Confirming the version helps ensure compatibility with your code and makes it easier to track down problems that might be caused by version-specific differences. The code uses TensorFlow's Keras tools to load the MNIST dataset, which is a standard collection of handwritten digit images for training image processing models. The loading function returns 2 sets of data, one for training and one for testing. The training set includes images and their labels, which are used to teach the model to recognize digits. The second set, containing test images and labels, is available for later evaluation, even though it is not used in this particular code snippet. This structure is a common way to prepare data for machine learning tasks, so models can be both trained and evaluated effectively. To show the effects of color jitter and noise, we start by choosing a small subset of the MNIST dataset. In this example, we select 8 samples and take the first 8 images from the training set. We store these images separately so we can easily visualize and test how the color jitter and noise transformations change them. Working with this small group of images keeps the demonstration simple and manageable. This code converts grayscale images into a 3-channel format similar to RGB by duplicating the single grayscale channel 3 times along the last dimension. It uses a repeat operation from a numerical library to copy the original channel. This step is important because many image processing methods require images to have 3 color channels, even when the original data is only grayscale. The code changes image pixel values to floating point numbers and scales them so they fall between 0 and 1. This process, called normalization, puts all input data on a consistent scale. Having inputs on a common scale is important because it helps many machine learning models train more effectively. It can improve both the performance and stability of the training process. We verify that our small dataset contains the correct number of samples by checking that the first dimension of the reshaped image array matches the expected sample count. This first dimension represents how many images we have. If the numbers do not match, the assertion fails and alerts us to a problem. This safeguard confirms that our data slicing and reshaping steps were done correctly and that the dataset size is consistent for further processing. We build a simple color jitter layer using a sequential model in TensorFlow to apply random brightness and contrast changes to images. The random brightness step adjusts image brightness by up to 0.2 within a normalized range from 0 to 1 and uses a fixed seed, so the randomness is reproducible. We then add a random contrast step that changes image contrast by a similar amount, again using the same seed for consistent behavior. Together, these operations simulate variations in lighting and contrast, which helps make models more robust when trained on the augmented images. We define a function that adds gentle Gaussian noise to images to create slightly altered versions. It first generates random noise with a mean of 0 and a small standard deviation, using a fixed seed so the results are reproducible. This noise is added to the original images, and the result is then clipped so that all pixel values stay within the valid range from 0 to 1. The function finally returns these clipped, noisy images. We begin by selecting a small batch of images from our pre-processed dataset, such as the first 4 images from a small RGB collection. These images are then converted into a TensorFlow tensor. This conversion is important because it lets us use TensorFlow's optimized operations for later steps. Once in tensor form, the images can be efficiently transformed or passed into a neural network for training or evaluation. We apply a color jitter layer to each batch of images in the sequential model, which randomly changes their brightness and contrast. This simulates different lighting conditions, so the model sees a wider variety of visual inputs during training. As a result, the model becomes more robust, and we obtain a new batch of images with these random color transformations already applied. After applying color jittering to a batch of images, we add Gaussian noise to further augment them. This is done by calling a noise-adding function on the already jittered images. The noise uses a standard deviation of 0.05, which sets how strong the noise effect is. The output is a new set of images that now include both the color jitter and the added Gaussian noise. We verify that the batch of images has the same shape before and after applying color jitter. This check confirms that the transformation has not changed the image dimensions. Keeping the shape consistent is important so that later processing steps can rely on the data having the expected size and structure. We use the matplotlib plotting library, specifically its pyplot module, to create visualizations in Python. In this context, it will allow us to display images from our dataset. By showing these images, we can clearly see how color jitter and noise transformations affect them. This visual feedback helps us better understand the impact of these pre-processing steps. We create a figure arranged as a grid with 3 rows and 4 columns of images, using a subplots function in matplotlib. The figure size is set to 8 by 6 inches, which controls the overall dimensions of the display. This grid layout lets us place the original, color-jittered, and noisy images in a consistent structure. As a result, it becomes easy to visually compare how each transformation changes the images. In this step, we display the original images by placing them in the first row of a grid. We loop through the first 4 images in the batch and show each one using a plotting function from the matplotlib library. Before displaying, we convert the image data to a NumPy array so it is compatible with the plotting tool. We also turn off the axis labels and ticks for each subplot so the viewer's attention stays on the images themselves. We now display the color-jittered images in the second row of our figure by looping over the first 4 images. For each one, we show it in the appropriate position in the subplot grid using a standard image display function. Before displaying, we convert the image from a tensor format to a NumPy array so it is compatible with the plotting library. Finally, we turn off the axes for each subplot so there are no tick marks or labels, keeping attention on the images themselves. In this step, we display images that have been modified with both color jittering and Gaussian noise. We take the first 4 images from the noisy batch and show them on the 3rd row of a plot grid using a standard image display function. Each image is converted to a format compatible with this function, and the axes are turned off, so there are no labels or ticks, keeping attention on the images themselves. The code assigns a title to the figure using the figure's title function. This title briefly explains what each row of images represents. The top row contains the original images, the middle row shows images with color jitter applied, and the bottom row shows images with both color jitter and added noise. The title's font size is set to 10 to keep it easy to read. The code first uses a layout adjustment function from matplotlib to make sure all subplots fit neatly in the figure without overlapping. It then calls the display function to render the figure window. This shows the original image alongside the versions with color jitter and added noise, allowing you to compare them clearly and in an organized way. This script shows how to perform image augmentation on a small subset of the MNIST dataset using TensorFlow. It loads grayscale images, converts them to 3 color channels, and normalizes their pixel values between 0 and 1. A color jitter operation then randomly changes brightness and contrast, and Gaussian noise is added on top, with fixed random seeds to keep the results repeatable. The original, color jittered, and jitter plus noise images are compared side by side to illustrate how these augmentations change appearance while preserving structure, which helps train more robust machine learning models. Label-safe augmentations. Label-safe augmentations are transformations that change the input data without changing what the correct label should be. In a cat versus dog classifier, operations like flipping, rotating, or adjusting brightness are safe because the image still clearly shows the same animal. In contrast, cropping that removes most of the animal is not safe because it might eliminate the subject and make the label unclear. A good rule is to think like a human annotator. If a transformation would make them hesitate or change the label, it is not label safe and should be avoided. Whether a data augmentation is label safe depends on the specific prediction task. An operation like flipping an image can be fine for general object classification, but wrong when the label depends on left versus right, such as a car's parking sign. Adding noise to audio may be acceptable for word transcription, but not for tasks that need precise acoustic details. And in medical imaging, small changes like slight rotations are usually safe, while larger ones that hide key features are not. The key is to understand exactly what the label represents and which visual or acoustic cues are essential. Then choose augmentations that preserve those cues and keep the labels valid. When designing label-safe data augmentation, you need to go beyond using popular transformations and make sure each one is consistent with your domain knowledge and annotation rules. Begin with conservative changes such as small rotations or mild color shifts that clearly do not alter the label. Then refine them based on validation performance. In areas like wildlife images, confirm that cropping does not remove the animal. And in document tasks, avoid masking text so heavily that it changes the topic. Regularly inspect augmented samples against their labels, and consult experts to ensure the transformed data still represents the intended truth. Python code, label-safe augmentations. This script shows how to apply label-safe image augmentations, meaning transformations that do not change the correct class of the image. It relies on TensorFlow's built-in image tools to perform simple modifications. The main goal is to expand the training data while preserving the original classification labels. The comment about installing TensorFlow is a reminder that this library must be installed before running the script. The script depends on TensorFlow to load datasets and perform image transformations, so it cannot function correctly without it. If TensorFlow is missing, you should use a package manager to install it. This prevents errors caused by missing dependencies and ensures the script runs smoothly. We begin by importing a few key modules from the standard library and beyond. The operating system module lets us work with files and directories and interact with the system. The random module provides tools for generating random values, which we will later use to control randomness with fixed seeds. We also import the numerical computing library NumPy to handle arrays and perform efficient mathematical operations throughout the script. We begin by importing TensorFlow, which provides the core tools for building and training machine learning models using tensors as the main data structure. We also import the datasets module from Keras, the high-level interface within TensorFlow, to easily access standard datasets. In this case, we will use the MNIST dataset to demonstrate image augmentations. These imports prepare the environment for carrying out deep learning tasks efficiently. We begin by setting a fixed seed value of 42 so that any random operations give the same results every time the code runs. We apply this seed to both the standard random library and to NumPy's random number generator. Doing this makes all random number generation consistent across runs. This setup is important for experiments, such as training and testing machine learning models, where reproducible results are required. We set the random seed in TensorFlow so that any operations involving randomness give the same results every time we run the code. This makes our experiments reproducible, meaning we can repeat them and get consistent outcomes. It also helps with debugging because we know that any changes in results come from changes in the code, not from random variation. Using the same seed across runs keeps the randomness in model training and data augmentation stable and predictable. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important for ensuring compatibility with other tools and for troubleshooting issues. By confirming the version, you can better understand and debug any problems that arise. We begin by loading the MNIST dataset using a helper function from Keras, which returns 2 sets of data. For this demonstration, we only use the first set, which contains the training images and their labels. The images are stored in one variable, and the corresponding digit labels are stored in another. The second set, which holds the test images and labels, is ignored because it is not needed here, and the underscore is used simply to discard that unused data. To quickly demonstrate the process, we work with a small subset of the MNIST handwritten digit dataset. We select 4 samples, taking the first 4 images from the training data and storing them together. We also take their corresponding labels and store them alongside the images. Using this small, manageable subset makes it easier to test our methods and clearly see the effects of data augmentation before applying them to the full dataset. The code prints the shape of the subset of training images to confirm that the data has been sliced correctly. This check verifies that the subset has the expected number of samples and the correct dimensions. By confirming the shape at this stage, you reduce the risk of errors in later processing steps that rely on the data being in the proper format. We first add a channel dimension to the grayscale images so they match the format expected by many image processing tools. Even though grayscale images have only one channel, they still need this extra dimension to be compatible with common functions. Using a function that expands the array dimensions, we turn each image from a two-dimensional array into a three-dimensional one. This prepares the data for later processing steps that require images to include an explicit channel dimension. We first convert the subset of images from NumPy arrays into TensorFlow tensors with a float32 data type so they work properly with TensorFlow operations. We then convert the labels, which are the target values for these images, into TensorFlow tensors with an int32 data type. Using these specific tensor types keeps the data consistent and compatible, which is important when preparing the dataset for model training or evaluation. We normalize the image data by dividing each pixel value by 255. This converts the original range of pixel values from 0 to 255 into a new range from 0 to 1. Putting the data on this consistent scale is important for many machine learning models. It helps the training process be more stable and can improve overall model performance. We define a safe augment function that takes an image tensor and applies small controlled changes while preserving the digit's identity. It first picks a random rotation angle between -0.15 and +0.15 radians and rotates the image using bilinear interpolation to keep the results smooth. Then it applies a slight random brightness adjustment to add variability without changing the label. Finally, it clips pixel values so they stay within the valid range from 0 to 1 and returns the augmented image tensor for further processing. In this part of the code, we define a function that rotates an image using TensorFlow's low-level operations. We first compute the cosine of the rotation angle to control how the image turns around its center. We then compute the sine of the angle, which works together with the cosine to describe the rotation. These two values are combined to build the transformation matrix that is applied to the image to produce the desired rotation. To build a transformation matrix for rotating an image, we arrange values into a 2x3 matrix using the cosine and sine of the rotation angle. The first row has the cosine of the angle, then the negative sign and a 0 to represent no horizontal translation. The second row has the sine of the angle, the cosine again, and another 0 for no vertical translation. These zeros complete the matrix in the standard format used for image transformations. The code reshapes the transformation matrix so it has the correct dimensions for later steps. It converts the matrix into a single row with 8 elements. This specific shape is required by the image transformation process. With this format, the rotation can be applied correctly to the image. To treat a single image as a batch in TensorFlow, you add a new dimension to the image tensor using the expand dimensions function. This extra dimension is placed at the start, turning the image into a batch of size 1. Many TensorFlow operations require inputs in batch format, even for a single example. Adding this batch dimension ensures the image is compatible with functions that process batches of images. This code uses TensorFlow's low-level image projective transform operation to rotate an image while keeping its original size. The image is first given a batch dimension, and a transformation matrix specifies how the rotation is applied. The output shape is set so the transformed image has the same height and width as the input. Bilinear interpolation is used to smooth the result, and areas outside the original boundaries are filled by reflecting the image, with any remaining uncovered regions assigned a pixel value of 0. The function returns the rotated image by removing the temporary batch dimension that was added for processing. It uses TensorFlow's squeeze operation to eliminate this extra dimension. As a result, the output image has the same shape as the original input image. This makes the rotated image ready for any further processing or visualization steps. We begin by creating an empty list to hold our augmented images. Then we loop through each image in the small dataset and apply the safe augment function to it. This function performs transformations such as rotation and brightness changes, while keeping the original label correct. Each transformed image is added to the list, gradually building a new collection of augmented samples. In this step, each augmented image is added to a list as the loop processes the small dataset one image at a time. Collecting all the augmented images in a single list prepares them for later batch operations, such as stacking them into one tensor. This also ensures that every transformed image is stored and can be easily accessed for comparison or further analysis. After we finish augmenting the images, we combine them into a single tensor using a stacking operation in TensorFlow. This gathers all the individual image tensors into one unified batch. Doing this keeps the data structure consistent, so the augmented images can be handled just like the original batch. As a result, it becomes easier to run further operations or make comparisons on the entire set of images at once. We first check and print the shape of the original batch of images to confirm its dimensions before applying any augmentations. This step verifies that the data has the expected format and size. Ensuring the input is correct is important for debugging and for understanding how the data moves through the augmentation process. We print the shape of the augmented image batch to compare it with the original batch and confirm that the dimensions are unchanged. This check ensures that the augmentation process has not altered the batch size or structure. Maintaining consistent dimensions is important so that later processing steps and model training can proceed without errors. In short, verifying the shape helps confirm that the transformations were applied correctly and safely. The code first converts the initial image in the original batch from a TensorFlow tensor into a NumPy array, so it can be inspected and manipulated more easily outside the TensorFlow environment. It then performs the same conversion for the first image in the augmented batch. By doing this, you can directly compare the original and augmented images to verify that the augmentations were applied correctly and that the associated labels remain accurate and safe. We start by printing a simple summary of the original image, showing its minimum and maximum pixel values. This tells us the range of pixel intensities present before any changes are made. Knowing this baseline range helps us compare the original image to its augmented versions and understand how the augmentation affects pixel intensities. To check that an augmented image is still valid, we compare it with the original by printing the minimum and maximum pixel values after augmentation. This lets us confirm that the pixel values remain within the expected range. By doing this, we ensure the transformations are label safe and do not distort the image so much that it becomes unrecognizable. The code prints the original labels of the dataset to confirm that the earlier data augmentations are label safe. In other words, even after transformations such as rotation or brightness changes, the identity of each digit is preserved. This ensures that the labels still correctly describe the corresponding images. Converting the labels to a NumPy array simply makes it easier to inspect and compare them with the augmented images. This script shows how to perform label-safe image augmentation in TensorFlow using a small subset of the MNIST dataset. It sets a fixed random seed for reproducibility, adds a channel dimension to the images, and normalizes pixel values between 0 and 1. The main function applies small random rotations and brightness changes that do not alter the correct classification labels, using a projective transform to implement the rotations. After augmentation, the script verifies that the original and transformed image batches have matching shapes and compares pixel value ranges for an example pair of images. It then prints the original labels to highlight that the augmentations preserve the label information. Integrating data transforms. Using transforms inside datasets. When you integrate data transforms directly into a dataset, each example is automatically prepared in the exact form your model needs. Instead of manually preprocessing raw data elsewhere, the dataset retrieves the raw inputs and labels, then applies steps like resizing or normalization as they are accessed. This creates a transformation pipeline that consistently prepares data according to your rules. As a result, your training loop can focus on optimization while the dataset reliably handles all data preparation. Applying transforms directly within your dataset is powerful because it keeps data access and preprocessing tightly connected, which reduces bugs and inconsistencies. For example, in a medical imaging project with chest X-rays of varying resolution and brightness, scattered preprocessing can lead to images being normalized or resized differently across training and validation. By centralizing all transforms in the dataset, every image, whether for training or testing, passes through the same pipeline. This makes it clear what the model actually sees, simplifies reproducing experiments, and ensures that all collaborators work with data in a consistent format. Using transforms inside your dataset lets you change how data is processed for different training phases while keeping the same way of accessing it. During training, you might use strong data augmentation, and during evaluation, you might switch to simple resizing and normalization. But the interface stays consistent. By allowing the dataset to accept different transformation pipelines, you can manage these changes in one place. This keeps the code cleaner and makes it easier to experiment with new data preparation strategies. Python code using transforms inside datasets. This script demonstrates how to apply data transforms directly within datasets using TensorFlow image dataset tools. It highlights how preprocessing steps can be built into the data pipeline itself, rather than handled separately. The main goal is to show an integrated approach where image transformations and model input preparation are combined into a single, efficient workflow. A line that begins with an exclamation mark is used as a command to install TensorFlow with the Python package manager pip. This command makes sure TensorFlow is available in the current programming environment. Including such installation commands and scripts is a common way to ensure all required libraries are present before the code runs. We begin by importing a few standard libraries needed for the script. The operating system library lets us work with files and environment settings. The random library provides tools for generating random numbers and making random choices. Finally, we import NumPy, a numerical computing library that helps us handle arrays and perform mathematical operations efficiently. We start by importing TensorFlow, which we need to build and train machine learning models. We also import image utilities from Keras, the high-level interface within TensorFlow, to handle image processing tasks. Together, these imports prepare our environment to load, manipulate, and transform image data efficiently for use in our models. We begin by setting a fixed seed value of 42 so that random number generation is consistent every time the program runs. We apply this seed both to the standard random library and to the NumPy random number generator. Using the same seed ensures that all random operations from these libraries produce identical results across runs. This reproducibility is important for reliable testing, debugging, and comparing experiments. We set the random seed for TensorFlow using a predefined value so that any random operations it performs will always give the same results each time the code runs. This makes the behavior of the model predictable and consistent. Such reproducibility is important for running experiments, comparing results, and debugging issues reliably. We start by printing the version of TensorFlow that is currently in use. This simple check confirms that the environment is set up correctly. It also helps ensure that the code will run as expected, since different TensorFlow versions can have different features or behaviors. The code sets the image height and width to 32 pixels each to keep the images small. This small size is chosen on purpose, so the program runs quickly, which is especially helpful with synthetic datasets or early testing. Using smaller images lowers both computation and memory demands, making it faster and easier to iterate and debug. We create a small synthetic image dataset by generating 12 images and organizing them into 3 classes. Each class represents a distinct category used to label the images. This setup provides a simple example of an image classification task. It is useful for testing and demonstrating how classification methods work on a manageable scale. We can create random images in TensorFlow using its random uniform function, which generates a tensor shape to match a batch of images. This shape specifies how many images we want, along with each image's height, width, and 3 color channels for red, green, and blue. The pixel values are filled with random numbers between 0 and 1, which mimics real image data. This is useful for testing image processing or machine learning pipelines without needing actual image files. To create a simple sequence of labels for a synthetic dataset, we use TensorFlow's range function to generate numbers from 0 up to the number of samples, not including the endpoint. We then apply the modulo operation with the number of classes, so the labels repeat in a regular cycle. For example, with 3 classes, the labels cycle through 0, 1, and 2 over and over. This method produces a predictable, repeating label pattern that is easy to understand and work with. Before building the dataset, the code verifies that the number of images matches the number of labels, so that each image has exactly 1 corresponding label. This check is essential for keeping the dataset consistent and reliable. If the sizes do not match, it signals a mismatch that could cause errors later in the data processing pipeline. We begin by creating a TensorFlow dataset from our images and labels using the Data API, which is designed to handle large datasets efficiently. This process slices the image and label arrays into individual elements so that each image is paired with its correct label. Setting up the data in this way is essential because it allows us to easily apply transformations and prepare the dataset for training and validation later on. We use a preprocessing function that takes an image and its label as input. The image is first resized to a fixed target height and width using TensorFlow, so that all images have consistent dimensions. Then the pixel values are normalized by shifting them by 1/2 and scaling by a factor of 2, which centers the data around 0 and helps the model learn more effectively. The function finally returns the processed image together with the original unchanged label. We define an augment example function that takes an image and its label, then applies simple random transformations to the image. It first performs a random horizontal flip using TensorFlow tools, with a fixed seed, so the randomness is reproducible. It then makes a small random adjustment to the image brightness, limited by a specified maximum change, to simulate different lighting conditions. These augmentations help improve the model's robustness, and the function finally returns the transformed image together with the original unchanged label. We create a validation dataset by mapping a preprocessing function over the original data, so that each image and its label are processed in the same way. This function resizes every image to a fixed height and width, and normalizes the pixel values. The mapping is done in parallel to keep data handling efficient. The result is a validation dataset with consistently pre-processed images that is ready for reliable model evaluation. To build the training dataset, we first pre-process each image and its label by resizing the image and normalizing its pixel values so the data is in a consistent format for the model. After this standardization step, we apply data augmentation to the preprocessed images. This augmentation randomly flips images horizontally and slightly changes their brightness. Applying these two transformations in sequence produces training data that is both uniform and varied, which helps the model learn to generalize better. We divide both the training and validation datasets into small batches of 4 samples to make processing more efficient. Using batches speeds up data loading, supports parallel computation, and helps manage memory usage, which is especially important for large datasets. Keeping the same batching strategy for training and validation ensures the data is handled consistently throughout the pipeline. We begin by taking a single batch of images and labels from the training dataset using the iterator, and we do the same for the validation dataset. The training batch contains images that have been both preprocessed and augmented, along with their labels, while the validation batch contains only preprocessed images and their labels. Inspecting these batches is important because it lets us confirm that the data pipeline is working correctly and that all transformations applied to the training and validation data are as intended. We begin by printing the shape of the training image batch to confirm the image dimensions and batch size. Then we display the training labels as a numeric array to verify that each image has the correct class label. We repeat this process for the validation images, checking their shape to ensure the data is structured properly. Finally, we print the validation labels to confirm that the class labels for the validation images are correctly assigned. Together, these checks provide a quick overview that the data batches are correctly formed and that preprocessing and augmentation have not disrupted the label assignments. This part of the code checks that the data transformations do not change the labels. It prints the first label from the training batch and the first label from the validation batch. By converting these labels to integers and displaying them, it verifies that preprocessing and augmentation have kept the original label values. This confirms that the dataset's labeling remains accurate throughout the transformation process. This script shows how to build efficient TensorFlow data pipelines by integrating preprocessing and augmentation directly into datasets. It first fixes a random seed for reproducibility and creates a small synthetic set of random images and labels. A preprocessing step resizes and normalizes the images, and an augmentation step adds random horizontal flips and brightness changes. One dataset is prepared for validation using only preprocessing, while another is prepared for training using both preprocessing and augmentation, and both are batched for efficient loading. When run, the script prints the TensorFlow version, batch shapes, and labels, confirming that only the images are transformed while the labels remain unchanged. Compose versus custom calls. When you use multiple data transforms, you can either apply each one separately or combine them into a single composed pipeline. A composed pipeline runs the transforms in a fixed order and treats them as one process, which helps keep preprocessing consistent across all samples. This consistency reduces errors and mismatches between training and validation data. It also leads to cleaner dataset definitions, easier reuse in different experiments, and a clearer understanding of how raw data becomes ready for the model. Using custom calls for data transforms gives you fine-grained control, but also adds complexity and risk. It lets you choose transforms dynamically based on sample properties, training stage, or model performance, enabling adaptive strategies. However, this scatters transformation logic across your code, making debugging harder and reducing reproducibility. It also raises the chance of mismatches between training and evaluation data, which can distort how you assess model performance. Choosing between composed pipelines and custom calls is about balancing structure and flexibility for your project stage. In stable production or large academic settings, composed pipelines are preferred because they are consistent, easy to audit, and make every data transformation clear and traceable. In early research, custom calls are useful for fast experimentation, such as quickly changing preprocessing steps. A good strategy is to begin with custom logic to explore options, then move to a composed pipeline once you have a reliable setup that your team can easily reuse and reproduce. Python code: compose versus custom calls. This script demonstrates how to compare composed transforms with custom transforms using TensorFlow's image preprocessing tools. The goal is to understand the differences between these two approaches rather than to optimize training speed or performance. As you listen, focus on how the transforms are structured and applied, and how TensorFlow utilities support this image preprocessing workflow. A line that begins with an exclamation mark is a command to install TensorFlow. It is commonly used in environments such as Jupyter Notebooks. This command makes sure TensorFlow is installed and available before the rest of the code runs. In other words, it is a setup step to prepare the required library for use in the script. We start by importing the operating system module so we can interact with the system, for example, to work with files. We also import the random module to generate random numbers, which is useful for tasks like controlling randomness with a fixed seed. Finally, we import NumPy, a numerical computing library that supports large, multidimensional arrays and matrices and provides many mathematical functions to work with them. We start by importing TensorFlow, a powerful library used for machine learning and deep learning. This gives us access to many tools for building and training models. We also import the Layers module from TensorFlow's Keras interface, which provides ready-made neural network layers. By stacking these layers, we can more easily design and construct complex model architectures. We begin by setting a seed value of 42, so that any random operations are reproducible and give the same results each time the code runs. We apply the seed to the random library, to the random number generator in NumPy, and to TensorFlow's random operations. Using the same seed across these libraries keeps all random behavior consistent, which helps ensure reproducibility in both data processing and model training. This line displays the version of TensorFlow that is currently in use. It provides a quick way to confirm which version of the library is loaded. Knowing the exact version is important because different versions may behave differently. This helps with checking compatibility and diagnosing issues during development or debugging. This code loads a small sample of the MNIST dataset, which contains images of handwritten digits commonly used to train image processing models. It uses a function from TensorFlow's Keras tools to retrieve the data, which is returned as two pairs of image data and labels. The first pair provides the training images and their digit labels, and that is what we use here. The second pair contains test images and labels, but it is not used in this example. Working with this subset keeps the demonstration simple and manageable, while still showing how the data is organized. To keep the demonstration simple, we work with a very small subset of the MNIST training data. We take just the first 8 images from the training set, along with their corresponding labels. This small batch of images and labels will serve as our example, and will be used to show how the preprocessing steps work in the rest of the script. The code prints the shape of a small batch of images to verify that the data has the expected dimensions. This check is important to confirm that the images are correctly formatted. Once the shape looks right, we know the data is ready for further processing. This simple step helps prevent errors later in the pipeline. The code adds a channel dimension to the grayscale images by inserting a new axis, changing each image from a two-dimensional array to a three-dimensional one. This extra dimension represents the image channel, even though there is only a single channel for grayscale. Many image processing tools require images to include this channel dimension. By reshaping the data in this way, the images become compatible with those functions and ready for further processing. This function builds an image preprocessing pipeline that first resizes each input image to 32 by 32 pixels. It then converts the image data to 32-bit floating point values and normalizes the pixel intensities by dividing by 255 so they fall between 0 and 1. After that, it applies a random horizontal flip using a fixed random seed so the transformation is reproducible across runs. The function finally returns the processed image. The custom preprocess function takes an image and an index, converts the image to floating point values, and normalizes its pixels to lie between 0 and 1. If the index is even, it resizes the image directly to 32 by 32 pixels. If the index is odd, it resizes the image to 28 by 28 pixels, and then pads it so it becomes 32 by 32, centering the smaller image. In addition, whenever the index is divisible by 3, it applies a random horizontal flip using a fixed seed so the result is reproducible. After these steps, it returns the processed image. We begin by creating a TensorFlow dataset from the small images and their labels, using a function that builds a dataset from tensor slices, which keeps the data compatible with TensorFlow operations. We then transform each dataset element with a mapping function that takes an image and its label, applies the combined preprocessing steps to the image, and returns the processed image with the original label. This mapping is configured to automatically tune the number of parallel calls, so TensorFlow can optimize performance based on the available computing resources. We build a TensorFlow dataset by first creating a sequence of indices that match the positions of images in a small batch. Then, we create another dataset from the images and their labels, where each element is a pair of one image and its label. We zip the index dataset with the image label dataset, so each element now contains an index along with its image and label. Finally, we apply a custom preprocessing function to this combined dataset, using the index to control how each image is transformed, and enable automatic parallel processing to improve performance based on available system resources. We take a small batch of 4 samples from the dataset that uses the composed preprocessing pipeline, so we can see how its transformations change the images and labels. Then we take another batch of 4 samples from the dataset that uses the custom preprocessing pipeline to observe how its transformations differ. By iterating over both datasets and comparing these batches, we can directly analyze and contrast the preprocessing effects of the two approaches. The code first separates the images and labels from the batch that went through the composed preprocessing pipeline. It then does the same for the batch processed by the custom pipeline. By unpacking these batches into images and labels, it becomes easy to access and directly compare the outputs from the two different preprocessing approaches. We begin by printing the shape of the image batch produced by the preprocessing pipeline to quickly confirm that the data dimensions are as expected for later processing or analysis. We then print the labels for this batch and convert them to a NumPy array so we can easily inspect their values. This allows us to verify that each image is correctly paired with its label. Together, these checks help ensure that the preprocessing pipeline preserves the integrity of the dataset. We begin by printing the shape of the custom image batch to quickly check the dimensions of the data produced by the custom pipeline. Then, we print the labels for this batch, converting them to a NumPy array so they are easier to read. Together, These steps let us confirm that the custom preprocessing pipeline is working correctly by verifying both the structure and the content of its output. The code first computes the average pixel value across all images in the composed batch using a reduce mean operation, converts this result to a float, and prints it with a label for the composed pipeline. It then repeats the same process for the custom batch, again calculating the mean pixel value, converting it to a float, and printing it with a label for the custom pipeline. Comparing these mean pixel values gives a quick sense of the overall brightness or intensity of images from each pipeline and helps reveal how their different pre-processing methods affect the data. The script ends by printing a message that confirms the comparison between the composed and custom image transformation pipelines has finished successfully. This final message indicates that all intended operations have run without errors. It provides a clear endpoint for the process and reassures the user that the entire script executed as expected. This script compares two image preprocessing approaches in TensorFlow using a small subset of MNIST digit images. It first sets deterministic seeds for reproducibility, then applies a composed pipeline that resizes images to 32 by 32 pixels, normalizes them, and randomly flips them horizontally. It also applies a custom pipeline that changes how images are resized based on their index, sometimes adds padding to keep the size consistent, and conditionally flips them. The script processes a small batch through both pipelines, prints the resulting shapes and labels, and reports the mean pixel values to highlight how the different preprocessing choices affect the images. It concludes by confirming that the comparison ran successfully. Transform effects on metrics. When you add transforms or augmentations to your data pipeline, they do more than change how the inputs look. They also affect training metrics like accuracy and loss. Adjusting transform strength can shift these metrics, even when the model and optimizer stay the same. Stronger image augmentations often raise training loss and lower accuracy at first, because the model faces more varied inputs. This does not necessarily mean the model is worse and can actually indicate better generalization. Understanding this relationship helps you interpret training curves correctly and avoid misjudging model performance. When training a model, it is important to distinguish between the transforms used for training and those used for validation and testing, because this affects how you interpret performance metrics. During training, you typically combine basic preprocessing such as resizing with random augmentations like flips to increase data variety, which may slightly lower metrics but improves robustness. For validation and testing, you should use only consistent preprocessing so that evaluations remain stable and comparable over time. If you apply strong augmentations during evaluation, accuracy can appear worse simply because the data is distorted, not because the model is performing poorly. Keeping the evaluation pipeline consistent allows you to reliably track true improvements or regressions in the model. Think of testing data transforms as an experiment where you adjust the transform pipeline and watch how the training and validation curves respond. Begin with simple preprocessing to record baseline metrics, then gradually add or strengthen augmentations. Focus on final accuracy, the shape of the learning curves, and the gap between training and validation performance. If moderate augmentations lower training accuracy but improve test performance, they are likely reducing overfitting, while very aggressive transforms that cause unstable metrics may be harming the data. By carefully logging your transform settings and comparing runs, you can see how each choice affects learning and make better decisions for real-world deployment. Python code. Transform effects on metrics. This script demonstrates how data transforms, such as simple augmentations, influence model performance metrics. It compares training runs with and without these augmentations to highlight their impact. The experiment is kept small and clear by using a tiny subset of the MNIST dataset, making it easier to focus on how the metrics change. The commented line recommends installing TensorFlow version 2.20.0. Using this specific version helps keep the code compatible with the rest of the script. Different TensorFlow versions can change how certain features work or how code must be written. Sticking to the suggested version reduces the risk of errors when running the program. We start by importing 3 key libraries. The operating system library lets us interact with the system environment, such as working with file paths. The random library gives us tools for generating random numbers, which is helpful for tasks like shuffling data. Finally, the numerical computing library NumPy allows us to work efficiently with arrays and perform fast mathematical operations. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras, so we can define the building blocks of our network, such as convolutional and dense layers. Together, these imports provide the essential tools needed to construct and train our model efficiently. We begin by setting a seed value of 42 so that all random operations are reproducible. We apply this seed to the random library, to NumPy, and to TensorFlow, so each of their random number generators behaves consistently. Using the same seed ensures we get identical results every time we run the code, which is essential for debugging and for fairly comparing different runs or experiments. This line of code prints the version of TensorFlow that is currently in use. It provides a quick check that the intended version of the library is installed. Confirming the version helps ensure that your code is compatible with the library. It also supports reproducibility, since others can match the same TensorFlow setup when running your code. Using Keras, we load the MNIST dataset through its built-in datasets module, which provides separate training and testing data. Each part contains images of handwritten digits and then matching labels. The training images and labels are stored together, and the test images and labels are stored together. This dataset is a standard benchmark for image classification, especially for recognizing handwritten digits. To quickly show how transformations affect our data, we first reduce the dataset size. We limit the training set to 4,000 samples and the test set to 1,000 samples. Then, we take only the first 4,000 images from the training data, along with their matching labels. This smaller subset makes it easier and faster to demonstrate the impact of the transformations. To speed up evaluation, the test dataset is intentionally reduced in size. The code selects only the first 1,000 test images and their labels, creating a smaller subset of the original data. This makes the evaluation run faster and is especially useful for quick demonstrations or when you just want to test the process without using the full dataset. We first print the shapes of the training and test datasets to confirm they match our expectations before building the final datasets. This quick check verifies that data slicing and preprocessing were applied correctly. By doing this, we ensure the model will receive inputs in the proper format and with the correct dimensions, which is essential for reliable training and evaluation. We first convert the training images to floating point numbers so they can be normalized properly. Then we divide each pixel value by 255 to scale all pixels into a range from 0 to 1, which is a standard preprocessing step for neural networks. We apply the same conversion and scaling to the test images to keep the data preparation consistent between training and testing. We add a new axis to the end of the training and test datasets so that each image includes a channel dimension. This step is required because convolutional layers expect image data to have a specific shape. In particular, convolutional neural networks typically take four-dimensional input: batch size, height, width, and number of channels. By adding the channel dimension, we make sure the image data is compatible with these input requirements. We begin by turning the training images and their labels into a TensorFlow dataset. This means organizing them in a structured way that TensorFlow can handle efficiently. With this dataset in place, we can use TensorFlow's data pipeline tools to manage, load, and process the data smoothly during training. This setup helps keep the training process efficient and scalable. We begin by shuffling the training dataset so the samples are in random order, which helps prevent the model from picking up unintended patterns. The shuffle uses a buffer as large as the dataset and a fixed random seed, so the random order is both thorough and reproducible. After shuffling, we group the data into batches of 64 samples. Batching allows the model to process many examples at once, making training more efficient and better using available computational resources. To create a validation dataset, we take the test images and labels and turn them into a TensorFlow dataset using the method that builds datasets from tensor slices. This organizes the data so it can be processed consistently during evaluation. We then group the data into batches of 64 samples, which means the model evaluates 64 examples at a time. This batching step is important for making the evaluation process more efficient on modern hardware. We define an image augmentation function that takes images and their labels as input and applies simple random transformations to improve training. It first performs a random horizontal flip using TensorFlow's image tools, with a fixed seed to keep the randomness consistent. It then slightly changes the image brightness within a small range to simulate different lighting conditions and make the model more robust. Finally, the function outputs the transformed images together with their original labels for use in the training pipeline. We expand the training data by applying a transformation function to each element of the original dataset using TensorFlow's data mapping tools. For each batch of images and labels, an image augmentation function introduces random changes, such as flipping and brightness adjustments. These operations are run in parallel with TensorFlow's automatic tuning to improve performance. This creates an augmented dataset that is richer and more varied for training the model. Prefetching is used to speed up the data pipeline by preparing the next batch of data while the model is still processing the current one. We apply prefetching to the base training dataset, the augmented training dataset, and the validation dataset. TensorFlow's auto-tuning feature automatically selects how many batches to prefetch, which reduces model idle time and improves overall training efficiency. We define a function that builds a small convolutional neural network in Keras for classifying MNIST digits. It uses a sequential model that takes 28 by 28 grayscale images as input, applies two convolutional layers with ReLU activation separated by max pooling, then flattens the result and passes it to a dense layer with 64 units. The final output layer has 10 units with softmax activation to produce class probabilities for the 10-digit classes. The model is compiled with the Atom optimizer, uses sparse categorical cross-entropy as the loss for multi-class integer labels, and tracks accuracy as the main performance metric, returning a ready-to-train model. We begin by training a small convolutional neural network without any data augmentation. We build the model, then train it on the original training dataset for 3 epochs, so it passes through the data 3 times. During training, we also use a separate validation set to track performance on unseen examples. while turning off detailed training logs. This baseline run will later serve as a comparison point for training the same model with data augmentation. We begin by creating a new small convolutional neural network using the model building function, then train it on the augmented training dataset. During training, we run for 3 epochs, so the model sees the entire dataset 3 times. We also provide a separate validation dataset to measure performance on unseen data after each epoch. The training is run in silent mode without progress messages. This setup lets us evaluate how data augmentation affects the model's performance. We begin by extracting the final epoch metrics from the training history of both models. For the model trained without augmentation, we retrieve its recorded loss and accuracy across epochs, and we do the same for the model trained with augmentation. By focusing on the metrics from the last epoch, we can directly compare how each model performed at the end of training. This comparison is based on both training and validation loss and accuracy, allowing us to evaluate the impact of data augmentation on overall performance. We compare the training and validation performance of 2 models, one trained without data augmentation and one trained with it. For each model, we look at the training loss and accuracy, then the validation loss and accuracy, using rounded values for clarity. By examining these 4 metrics for both models, we can directly see how data augmentation affects overall model performance. This script compares training a convolutional neural network on a subset of the MNIST dataset with and without simple data augmentation. In one setup, the images are randomly flipped horizontally and slightly adjusted in brightness, while the other uses the original images only. Both models are trained for 3 epochs and then evaluated on a validation set. The model trained with augmentation often shows slightly better validation accuracy and lower validation loss. This demonstrates that even basic transformations can improve generalization by making the model more robust to variations in the input data. In this lecture, you learn to apply common preprocessing transforms such as normalization, resizing, and tensor conversion to raw data. Design and configure data augmentation pipelines that improve model robustness without corrupting labels. And integrate transforms into dataset and data loader workflows while monitoring their impact on training. In the next module, Module 5, we will go over computer vision models.
Thank you for your attention. See you all in the next lecture.